Welcome to the Explainer. We are jumping right back into the elemental foundations of carbon chemistry today. We're going to dive into the truly elegant logic of how the fundamental building blocks of the universe snap together to create, well, literally the entire world around us.
So think about this for a second. What do you, the pencil sitting on your desk, and a flawless billion-year-old diamond have in common? I mean, on the surface, absolutely nothing, right? One is a living, breathing human, one's a fragile writing tool, and the other is literally one of the hardest and most expensive materials on Earth. But down at the microscopic level, they share the exact same foundational architecture.
Here is our roadmap for answering that. 1. We'll meet carbon. 2. We'll explore covalent bonds. 3. We'll look at catenation. 4. We'll talk about carbon in our daily lives. And 5. We'll wrap it all up with a summary.
All right, let's get into Section 1. Meet carbon, the ultimate element.
Now, if the periodic table were a massive toy box, carbon is for sure the ultimate, most versatile Lego brick inside it. And the real secret to its superpower, it all comes down to the number 4. You see, in the atomic world, stability is everything. Carbon has exactly 4 electrons in its outermost shell. But to achieve perfect stability, an atom usually wants a full shell of 8. So this leaves carbon halfway there, basically craving exactly 4 more electrons to complete its set. And that brings us to the concept of tetravalency. Tetra meaning 4, and valency referring to its bonding capacity. Because of this, carbon acts almost like a central hub with 4 distinct connection points, all ready to snap on to other elements simultaneously. It isn't just limited to connecting to 1 or 2 neighbors. It can literally hold hands with 4 different atoms at the exact same time. Moving right along to Section 2, the magic of covalent bonds, or sharing is caring. When it comes to bonding, elements usually rely on 2 main strategies. Some elements selfishly take or completely give away their electrons to create those magnetically charged ionic bonds. But carbon? Carbon's a team player. It prefers a much more collaborative approach called covalent bonding, where the atoms actually share pairs of electrons. So, a covalent bond forms when 2 atoms share pairs of electrons to achieve a stable electron configuration. By sharing these electrons rather than transferring them entirely, carbon can form incredibly stable, super diverse partnerships. Honestly, it's kind of like the atomic equivalent of a potluck dinner. Everyone brings a little something to the table, and everyone leaves completely satisfied without having to expend unnecessary energy. Let's break down the logic step by step. First, carbon just wants stability, like any other element. Second, gaining or losing 4 entire electrons, that requires a massive, almost impossible amount of energy. So third, it completely avoids that high-energy nightmare by opting to just share its 4 valence electrons with its neighbors. It gets to borrow theirs, they borrow carbon's, and boom, everyone is stable. Now, because these electrons are locked in these sharing agreements, rather than creating strong electrostatic charges, covalent compounds usually have pretty low melting and boiling points. Basically, the bonds between the molecules are relatively easy to break with heat. On top of that, because there aren't any free-floating charged particles hanging around, they are remarkably poor conductors of electricity. Okay, Section 3. Catenation, building long chains.
Catenation is basically just a fancy science word for carbon's absolute favorite party trick, forming bonds with itself. While other elements might manage to form a fragile little chain of 2 or 3 atoms before falling apart, carbon can link up by the hundreds or even thousands, creating massive, incredibly stable molecular structures.
And because it has those 4 connection points we talked about, carbon atoms don't just snap together in boring straight lines.
They can form complex branch chains that look like tree limbs, or they can even loop back around on themselves to form intricate multi-sided rings. This kind of structural versatility is totally unmatched on the periodic table.
Oh, and this ability to bond with itself in all these different patterns, that beautifully answers our question from the very beginning. The hard, sparkling diamond and the soft, slippery graphite inside your pencil, chemically speaking, they are totally identical. Both are 100% pure carbon. The only difference is the catenation. In a diamond, the carbon atoms form this super rigid 3D network. But in graphite, they form flat hexagonal layers that easily slide right over one another. Same exact elemental Lego bricks, just a completely different architecture.
Which brings us to Section 4, Carbon in our daily lives, compounds all around us. By pairing just a few carbon atoms with basic elements like hydrogen and oxygen, we get entirely different functional materials. Methane gives us natural gas to fuel our homes. Ethanol is used for medical solvents and beverages. And acetic acid, that's what gives you the vinegar sitting right there in your kitchen. But honestly, it goes so much further than just gas and vinegar. It is no exaggeration to say carbon is the backbone of human existence. The carbohydrates and proteins in your food, the cotton and synthetic fibers in the clothes you're wearing right now, the pharmaceuticals we take, the plastics we use every single day, all of it relies entirely on carbon's ability to form diverse, stable, covalent bonds. Let's bring it all home. Section 5, a summary of carbon concepts, reviewing the building blocks. Just to quickly recap our explainer today, the core takeaways are wonderfully straightforward. Carbon relies on a valency of 4, that's tetravalency. It bonds by sharing electrons through highly efficient covalent bonds. It links to itself to form these massive structures via catenation, and ultimately, it is the structural basis for practically every material we interact with daily.
So as scientists continue to unlock the secrets of wonder materials like graphene, carbon nanotubes, and push the boundaries of synthetic biology, I'll leave you to ponder this. If carbon's unique rules literally built life itself, what incredible, mind-blowing innovations will humanity construct from it tomorrow? Thanks so much for joining this explainer.